Okay, so in this lecture, we're talking about forces in motion, and this is kind of the first lesson where we're introducing what a force is and going through that, and this would be for my junior and senior level physics class. So, we start off with pushing a paper clip around on our desk, and so we see each vector that we've drawn representing our forces of motion. And then I've listed through whether the motion was described as a push or a pull. And so we get into the idea that a force is considered a push or a pull exerted on an object. That force causes an acceleration. Okay? And then we talk about two basic types of forces. The first force is a contact force, and that's when the two objects, the one applying the force and the one receiving that, are in contact with each other. And then the second one is a field force. It's one in which the force is exerted without touching. Like gravity, we feel Earth's gravity even if we're not touching the Earth. And so when we start describing forces, we start looking at free body diagrams. And that's just a model that shows forces acting on a system. And so we start with some basic forces. And so on the first picture, I have an apple hanging on a tree. You can kind of see my tree and my apple. And so we have the force of gravity, which is always pointing down, and we have the force of the tree pulling up on the apple. The reason why the apple doesn't fall down is because the force of gravity and the force of the tree are equal to each other. And so when we look at a child pulling a wagon, we see the force of the kid pulling to the left. We see the force from the surface of the earth pushing up and the force of gravity pushing down. Now, we can see that the wagon wouldn't be traveling up or down, and so we see that the force of the earth and the force of gravity going in those opposite directions would be equal to each other. I want you to take a moment and draw a man standing in a box and add in the forces, and then also draw a sign hanging from a pole and add those forces in. Alright, so what happens to the motion of an object when a force is applied? The force causes a change in motion of the object. It can change the velocity, so it causes an acceleration, or it can change the direction, cause it to turn, or it can do both. It can slow it down, speed it up, and change its direction. Okay? Two objects. The second object is pushed with twice the force of the first, which object will accelerate faster. In this case, the second object will accelerate faster because it has a bigger force applied. So the idea is that more force causes a greater acceleration. Alright, again, we're looking at two objects with different masses this time. The mass of the first object is double the mass of the second. Both objects are pushed with the same force, which will accelerate faster. In this case, the second object will accelerate faster because it has less mass. So the same force applied to a smaller mass will cause a greater acceleration. It will have a greater effect. And so we see our first major equation in this section, which is that force equals mass times acceleration. F equals m times a. In the past, I've had people switch m and a around, and so they kind of spell out the word fam, and that's typically how it's remembered. Fam. F equals acceleration times the mass. And so we go back and we remember that the units of mass are kilograms, and that the units of acceleration are meters per second squared. And whatever we do to our numbers, we do the same thing to our units. And so we have kilograms times meters per second squared. And so 1 kilogram times 1 meter per second squared gives us newtons, which is our unit of force. Newtons, capital N. If we remember, forces are considered a vector unit, something that has both a magnitude and a direction, and so that those must be added or subtracted, assuming they're in those opposite directions, same direction or opposite directions, the one-dimensional direction, right? And so we have 2 newtons to the right and 2 newtons to the right, and we result with 4 newtons to the right. We would add them, right? And in this case, we have 4 newtons to the right and 2 newtons to the left, and so one of those forces would technically be negative, pointing in the negative direction, and we end up with 2 newtons as our resultant. Looking at a couple practice problems, we have a man pushes a box north with 95 newtons, and a boy pushes a box south on the same box with 24 newtons, what is the net force? And so when we're talking about net force, we're looking at the overall force applied to the box. And so we can see north and south. One of those is technically considered negative, so we would have 95 minus 24 newtons to give us an overall net force of 71 newtons north. Again, notice that we include the direction as this is a vector value. A man pushes a block east with 49 newtons and his wife pushes east with 78 newtons. What is the net force? Draw a free body diagram. So we draw the diagram, and both forces are described as applied east, and so they're pushing in the same direction. So they're both positive. We add them together, and they are 127 newtons east, again including that direction. A man pushes a block east with 49 newtons, and his wife tries to help by pushing west with 78 newtons of force. What is the net force? Draw a force diagram. So I didn't draw the diagram here. You can add that in. But again, we have a force east and a force west, which puts them in opposite directions. In this problem particularly, I have defined east as being negative, so we see a negative 49 newtons plus a positive 78 newtons to give us 29 newtons west. Now the reason why I ended up with west is because my positive direction is considered west. With a positive answer, I have a direction of west. So we get into Newton's second law of motion, and it states that the acceleration of an object equals the net force. And that is a pretty important word in this because it takes into account all forces we've discussed affecting the object divided by the mass of the object. So acceleration equals force divided by mass. This goes back to that same equation. It's just a way to rewrite it. It still would show the FAM kind of setup. F equals m times a. This is just a different format. So in the first problem, we see a 10 kilogram ball would require what force to accelerate down an alley at a rate of 3 meters per second squared. So I've rewritten the equation to solve for the force value, and I have mass times acceleration. And so I have 10 kilograms times 3 meters per second squared to give 30 newtons. Okay? What is the net force required to accelerate a car at a rate of 2 meters per second squared if the car has a mass of 3,000 kilograms? We're solving for force again, so we see force equals mass times acceleration, mass of 3,000 kilograms. Please note, make sure you're using the kilograms unit, times 2 meters per second squared. We get 6,000 kilograms meters per second squared, or 6,000 newtons. In this problem, we're solving for mass. What is the mass of the falling rock if it produces a force of 147 newtons? Ignore air resistance. And so the force applied from the rock is 147 newtons. The rock is falling, and so we use the acceleration due to gravity, which is 9.8 meters per second squared. If we were to rewrite the equation, we would find mass is equal to the force divided by acceleration. And so we would get the force, 147, over the mass, 9.8, and we would get 15 kilograms. 15 kilograms for the mass. We're going to backtrack just a little bit. We often sometimes kind of look at Newton's laws out of order, just because the second law is one of his most common laws of motion, and it's the equation one, so it's kind of where we like to start. However, his first law of motion states that an object at rest will stay at rest, and an object in motion will stay in motion unless acted on by an outside force. So if we create a net force on the object, we change what happens to the object. And so we talk about inertia because Newton's first law is often related to his law of inertia. And that's the tendency of an object to resist change in motion, not a force. Okay? Equilibrium is when the net force acting on the object is zero, meaning the forces in all the directions are equal. Okay? So in the first picture we see equilibrium because I have 2 newtons in opposite directions. When those are combined, we have a 0 Newton force, and that's no net force. Same thing with the second picture. In the third picture, equilibrium is not reached because I have unbalanced forces. So I have 6 newtons in one direction and 2 newtons in the other direction, which means I have a net force. My object will move or change its motion in the same direction as the 6 Newton force is applied. We just have a few types of forces that we like to talk about, and that is the force of friction, and that's just a force that acts, it's a contact force that acts in the direction opposite of the motion, and it's typically parallel to the surface, opposite the direction. Then we have our normal force. This is one of the most important forces. We will see this one come back a lot. It's the force exerted by the surface of an object it's resting on, so typically like the earth, and it's perpendicular to the surface in the direction away from the surface. It's always perpendicular to the surface no matter the angle of the surface. So if we were on an angled inclined plane, it would still be perpendicular from that inclined plane. We have the spring force. It's a restoring force. That is why a spring wants to kind of come back together. So if you pull on a spring and it snaps back, that's the spring force, and it's opposite in the direction of the displacement. So it kind of changes depending on how you're moving the spring. Tension force, it is created in a string when we pull on a string. Okay, or like if you're swinging a mass on the end of a string, the force within the string is considered the tension force, and it's away from the object, parallel to the string. We have the thrust force, force that causes the object to move, and it is the same direction as the acceleration of the object, not one we focus on a lot. And then we have our weight, which is our force of gravity, force due to gravity, straight towards the center of the object, causing gravitational pull.